the normal probability distribution is the most important of, well, is one of the most important probability distributions in statistics, and it's used to describe a continuous random variable. And it is widely used in statistical inference, so things like hypothesis testing, confidence intervals, and p-values, the mathematics and the concepts involved all follow from the ideas laid out when you study the normal probability distribution. So it's quite important to know that have a good understanding of the normal probability distribution when you're before all of this. So hypothesis tests, confidence intervals, and p-values. Let's just look at a few quick examples of where we might use it. So the heights of people, scientific measurements, they are in very quite often those can be well described with the normal distribution. Test scores and amounts of rainfall, quite often they can be assessed with the normal probability distribution or modeled by the normal probability distribution, but it's a good idea to test your assumptions as well. We'll talk about testing these assumptions later on. So the normal probability density function, that's quite an impressive looking mathematical formula there. But let's just break it down into its components. So we have mu, the mean. Let's write that down, mu. And we also have sigma. And mu and sigma are the mean and standard deviation respectively. We also have these two mathematical constants, which we won't look at so much. So the key components of that formula are mu and sigma. So that's the sort of key step we're just making here. So just as a quick remark, we're going to revisit this later on. What is the probability distribution function about? It is essentially the height of the curve. So suppose the curve looks like this. It is the height of the curve at x. So this is f of x here. Okay, so it's a mathematical formula that if you put in the value x here, it'll tell you the height of the curve there. So we'll come back to that later, some other time. So again, these two things are mu and sigma. So let's move on there. Now, the distribution of the normal probability distribution is symmetric. That's an important matter. We also sort of say that the skewness measure is 0, which is sort of another way of saying it's symmetric. Now, here we have the curve here. Just as a quick remark, we would call this the bell curve quite often because it has a sort of very obvious bell shape. Now, I'm going to sort of put a line down the middle here. Now, this is actually, so it's not a very straight line. Well, you get the idea. So, it's a bit hard to draw with this marker. So, essentially, what is to the left of that red line and is the mirror image of what is the right-hand side of that red line. So, that's the idea that the curve is symmetric around the mean. That gives rise to a very important rule that will come up later on, this idea of symmetry and the symmetry rule. So essentially that one side is the mirror image of the other. Again, the skewness measure is 0, and a lot of statistical output you'll be given. If you're running an analysis, it will tell you the skewness measure, which is, you sort of might pick up on it and sort of see, is that reasonably close to 0. So let's move on from that. So the entire family of normal probability distributions, so it's not just one probability distribution, so we're going to see this very shortly, that there's an infinite number of possible ways you could have a normal distribution. But there are two key parameters, and one is the mean, mu, and standard deviation, sigma. Okay. Now, so as I sort of mentioned there earlier on, so the mean here, it tells us where this central line is located on the number line. Okay, it's a bit better of effort of a red line. And also it's defined by the standard deviation sigma. So I'm going to sort of explain how these two things are used as we go along. So the highest point of the curve is at the mean, which is also the median, and the mode. So it's the mean, but it's also the median. And the idea of the median is that 50% of the values are less than the median and 50% of the values are greater than the median. And also we've sort of said that it's symmetric. Okay, so let's just keep a mental note of that. This is mu, which is the mean, but it's also the median. It's also the mode as well, but that's the highest point. And but again, that's not really as useful in this type of analysis. In other types of analysis, knowing what the mode is a bit more important. Not so much this time around. So the mean can be any positive number. It can be negative, 0, or positive. So it can be anywhere in the number line. Okay, so minus 10, 0, 20. For example, the average heights of people, let's say it's around 1.65 meters. So that will be the mean there. The heights, the weights of horses could be like something like, how much would a horse weigh? Let's say about 40 stone. Don't know. So, okay, so it can be anywhere in the number line. Now, this is more quite important actually. So, we've seen what the mu does, the mean. Now, it tells us where it is centered, but the width of the bell curve is determined by sigma, which is the standard deviation. So, larger values result in wider, flatter curves. Smaller values of the standard deviation return the opposite, very narrow but very high curves. So we have it there. So sigma equals 15, and in blue there, and in white we have sigma equals 25. Now the idea is an important thing to remember is the height under both of those curves, both of them is equal to 1. Okay, it's just sigma determines how spread out the values are from the mean, and here the mean is the same for both. Let's move on from that. Oh, we've gone too far. So, oops. Probabilities for the normal random variable are given by the area under the curve. Now, the total area under the curve is 1. That's an important matter when you're dealing with continuous probability distributions, which include the normal distribution, that you would sort of model, you would sort of construct a curve to represent the probabilities and intervals of probabilities. And the total area under the curve is 1. And just going back to that remark about the mean, or the highest point there, mu being the median, is that if you think about what the median is, 50% is less than the median, and 50% is greater than the median. So we have 0.5 to the left of the curve, and left mean of the mean, which is the left hand side of the curve, and 50% or 0.5 to the right hand side of the curve. Okay, and so that is quite handy to remember sometimes if you're using a sketch to sort of come up with get an idea about the probabilities. It's actually a sketch like that is really helpful to get your head around quite a few problems. So these are a few important things that we might remember. Now you don't have to remember these numbers here, but precisely to that 2 decimal places, but I have a rough idea. So 68.26% of values of the normal random variable are within plus or minus 1 standard deviation of its mean. 95.44% of the values are within plus or minus 2 standard deviations of the mean. 99.72% of values are within plus or minus 3 standard deviations. So it's 1, 2, 3. So this is actually often called, it's a sort of rule of thumb. Now it's actually something when you start working with tables, statistical tables, you'll actually be able to sort of do this from first principles. But it's actually handy to remember this as the 98, 95, 99 rule, which is within 1 or plus or minus 1 standard deviation, plus or minus 2 standard deviations, plus or minus 3 standard deviations. It's well worth having that as sort of as something that you just would it be able to cite if needed. When we look at the curve, this is the bell curve again. This is what it looks like. So remember that 100% of the values are the entire area in the curve represents 100%, 1 or 100%. Now within plus or minus 1 standard deviation, we would have 68.26% of the values. Okay, so that would correspond to, let me just shade it in here a bit. So this area here, which is bound by plus or minus 1 standard deviation, that would represent 68.26%. But you get off quite often, you get away with just sort of saying 68%. If we were to sort of, and that's between minus, mu minus 1 sigma and mu plus 1 sigma. Okay. If we were to sort of extend the idea further, talk about two standard deviations. Let's add in this bit here and this bit here. So 95% are, when we include the red area as well, is bound by mu plus or minus 2 sigma. And likewise for 3 sigma, 99.72% here and here. Just as a sort of remark, actually, it's sort of important to remember that there is very slight areas, very tiny areas, beyond plus or minus 3 sigma. So mu plus 3 sigma or mu minus 3 sigma. So very tiny area outside of that range, plus or minus 3 sigma. But it is there, and it's actually something well worth being mindful of. So we're going to come back to that. Now that's actually sort of setting out a rule of thumb and looking at it in the context of the bell curve. But what is going to happen there is that we were going to come back to that and look at it from another approach using statistical tables. So I don't like sort of saying learn this stuff off by heart, learn that stuff off by heart, but you can sort of do it from first principles. But if you do remember that what do you call it, the 68, 95, 99 rule, it is sort of worth remembering. I'm going to pause it there, and I'm just going to set up for part B of this presentation.